My talk is based on joint work with Alexey Bondol, Sergey Guminov, Anna Kocherova. I will tell about very simple things. Firstly, I would like to recall some concepts from quantum mechanics. Let V be R plus one dimensional. Yes. Okay. Okay. I'm waiting for you, but. Okay. Okay.
Because I wrote to you that we start here a little bit later. So let me introduce our speaker, Ilya Danovsky from MIPT, Moscow Institute of Theoretical Physics. And his talk is about collections of orthogonal projectors. He's working with Bondol,
Sergey Guminov.
Guminov, yeah. And I think this will be interesting to many participants because it is a mixture of symplectic algebraic geometry and also family operations.
Thank you very much. Firstly, I will recall some quantum story. What does it mean? Okay. Let V be R plus one. Okay. Okay. Vector space over complex number with Hermitian metric. It is well known that quantum states are vectors from V such that of norm 1. If we have two quantum states, then transition probability from V to W is transition probability is a square of inner product. So it's well known things. There are many unsolved problems in this subject. For example, the following: the problem of so-called mutually unbiased basis. Mutually unbiased basis. It will be motivation of my talk. So I will recall what does it mean, mutually unbiased basis. If we have two orthonormal bases from V, they called mutually unbiased if mutually unbiased. I will use the following brief denote. I will denote it itself. If if we have the following condition for any ij. The problem of mutually unbiased basis is the classification of this basis up to unitary equivalence classification. It's unsolved problem, and this problem is very hard. There are some partial results. Okay,
Can you not erase the last line, okay?
sorry?
Can you not erase the last line?
Okay,
Yeah.
maybe
Definition needs
here,
to be
okay? Okay.
Unbiased.
Okay, okay. So I will recall some partial results. If r plus 1 is 2, then a mutually unbiased basis is unique up to unitary equivalence. If r plus 1 is 3, then oops, 2. There is a 2 moops up to unitary equivalence. If r plus 1 is 4, there is a one-dimensional family. Of moops. If r plus 1 is 5, then finite set of these moops. If r plus 1 is 6, then there is a four-dimensional family of moops. In this case, this is partial result 2 because there are some finite set of isolated points. If r plus 1 is greater than 6, there are no classification.
No results?
No classification. There are some partial results. There is a site in internet where you can find this partial result.
Are there always isolated points?
In this case, yes. There is a
case greater than 6?
no. There are many. In the case r plus 1 is 7, there is a one-dimensional family, but many investigators think that there are two-dimensional, but they can find it. It's two-dimensional family. It's very hard problem because you have to solve some big system of equation, but non-linear. Yeah.
But why dimension 5 is exceptional?
Okay, because it's prime. So maybe in this case, early was there was some conjecture that if r plus 1 is prime, then maybe there is a finite set, but it was not true because in when r plus 1 is 7, there is a one-dimensional family. It's a quantum story. It's motivation from quantum mechanics. Now I would like to speak about, to tell about algebraic geometry story. if we have there is a reformulation of quantum story in terms of projectors. I would like to tell about it. Let V be R+1 dimensional vector space. With Hermitian matrix SEL, and assume that AI and Fj move is a pair of moops. Let us consider Hermitian projectors corresponding to EI. Pi is Hermitian projectors. Corresponding to EI. It means that image of Pi is EI. Analogously, Qj corresponding to EI. Hermitian projectors of rank 1, of course, corresponding to Fj. What does it mean in terms of projectors? The square of inner project. It's well known. It's usually that it is trace Pi Qj. So we can formulate the following algebraic problem in the terms of projectors. I would like to formulate it in these terms. Assume that we have complete collection of orthogonal projectors of rank 1. No, it means that sum of Pi is identity operator. And Qj, analogously Qj. And the algebraic problem is a classification of these pairs, of these sets of complete orthogonal projectors with the relation, satisfying the relations trace Pi Qj is 1 divided by R+1. Classification up to action of general linear group.
Action by conjugation.
Yes, of course. If this in quantum situation we classify it up to unitary group, and this case, oh sorry, R+1. So we have.
Why do we have on the left we have unitary group, and on the right we have general linear group?
Yeah.
So
It's
unitary group acts on basis. Right?
Yes, of course. Unitary X.
In notation we apply unitary group to projectors, and that will be confusing.
Of course, yes. Unitary group acts on this basis, of course. In this case, general linear group acts by conjugation, of course. So you're right. So it's algebraic problem. It's okay. Now I would like to speak about some generalization of this situation. Consider very simplest very simple things. The sets of two orthogonal, complete orthogonal projectors of rank 1. Complete orthogonal projectors. Complete set of orthogonal projectors. Without this relation. This set of projectors has the following geometric description. Firstly, we have the following description, geometric description. As we know, the image of any projectors is one-dimensional. One-dimensional subspace of V are parameterized by projective space, projectivization of V. So we can consider the following correspondence. Pi corresponds to points which I denote by a big letter. Okay. In this PV, in projectivization of V. As we know, a projector is defined uniquely by its image and its kernel. So point in this correspond to image. Using orthogonality, we get that kernel of Pi is a subspace generated by other points except Pi. So complete set of orthogonal projectors is defined uniquely by sets of points in projective space, PR. I will denote it by this. Analogously, the second set of orthogonal projectors, we have the 2R plus 2 points in PR. So these sets of points define two pairs, two complete sets of orthogonal projectors of rank 1 acting in V.
And what is the condition that these projectors
orthogonal?
I mean, yeah, that they are
Orthogonal means that kernel Pi is correspond to subspace generated by this one dimension.
Means that just a number.
Yes, yes, of course, it's important. Yes. Consider some examples. Examples and some statement.
The kernel. I see. The image actually is.
Image Pi. Okay. Image Pi is correspond to point. Yes. Consider the following case: R plus 1 is 3.
What's about the field? Ground field is essential?
Ground field. Yes. Okay. C. Yes. All is about. All is over C. Okay.
C.
Okay.
I mean, can we consider Q, for example?
Oh, maybe it's. I don't know what does it mean in this case. Okay. So I consider only all over complex number. Maybe it is interesting when we consider it in rational numbers, but I don't know the story in this case. So consider the simple case. R plus 1 is 3. In this case, we have 6 points. In projective plane. So we can consider some connection between geometric of these 6 points and some condition on projectors. For example, what does it mean that Q1 P1 is 0? It means that image of P1 is in kernel of Q1, sorry. And in terms of 6 points, it means that P1 is on the line through Q2 and Q3. So using this corresponding Q2 line through Q2, Q3 correspond to kernel Q1. And this condition means that P1 is in this line. So we can consider another degeneration.
So what is the condition? P1 is in the line through Q3 and
Q1, P1 is 0. It means that point P1 is in the line Q2, Q3. P1 is image.
Right.
P1. Kernel Q1 is correspond to line through 2 points Q2, Q3.
I'm not very well versed in
Uh,
projective geometry. So, these two bases are different. There is no assumption about the mutual positions of Pi and Qj except for the trace condition. That the trace is equal.
okay,
trace
without
of
this,
the product is equal to
this is not condition. We can consider this condition. We only consider 2 complete sets of orthogonal.
Okay. But why do you say that then Q1 and Q2 and Q3, the line passing through Q1 and Q2 and Q3 contains P1? There is no, I don't see this.
So kernel.
There is only one assumption.
So maybe I
that
did,
P1, P2 and P3 constitutes a basis.
yes. What P1, P2, P3. Yes.
And there is no reason. Why do you assume that P1 belongs to the line through P3?
This condition is clear. Okay.
This condition is not clear.
Yeah.
Oh, wow. Well, Q1, P1 is 0. It means
But
the
this
whole.
condition is not some. The trace
Okay.
is equal to 0.
Is it true?
And the trace is equal to 0.
No. So we are not consider condition of.
Different example. This is just some totally different problem.
Okay, we will return to this, but now we consider only this situation.
So we have Q1, P1 is equal to 0 if and only if the image of P1 is in the kernel of U1,
Okay.
right?
Okay.
So
It means that P1 is in the line
so the kernel of
through.
P1, the kernel of Q1 is the line from Q2 and Q3, right?
Okay. So we can consider the following degeneration. Assume that there is a conic through these 6 points. As we know, there is a conic through 5 points, but the following condition is a degeneration of configuration of these 6 points. There is a conic through this, some kind of degeneration. Okay. So what does it mean?
Like it with Pascal theory.
Okay, yes. Oh. What does it mean in terms of projectors? In terms of projectors, it means that I would like to formulate this degeneration as follows. Consider subspace generated by all commutators in space of matrices. So Okay. Thank you very much. So we can say that this subspace have dimension not greater than 4, because sum of Py is identity operator and sum of Qj is identity operator 2. We can express P3 through P1 and P2, and so we get this inequality. So what does it mean that?
What is this? These brackets. What do these brackets mean?
It means that a subspace are generated by this subspace in this.
Matrices.
No,
Maybe
not
use
matrices.
square brackets then.
Okay. Okay.
I mean the square brackets.
Okay. It's I consider the subspace in matrices generated by all commutators.
All commutators, nice.
Okay. All commutators. There are 9 commutators, but they are linear dependent. So we can this inequality is always true. But what does it mean that 6 points are on the conic? There is a conic through P1, P2, P3, P1, P2, P3, if and only if dimension of commutator subspace is not greater than 3. For example, it means that there are complex number xij such that zero, for example. It means that there is some linear combination of these commutators which is equal 0. So I would like to tell two, because we can describe P3 through ID and P1, P2. Okay, yes, always, but this condition means that. Okay. Okay, yes. Xij, okay. I'm not 0 always. Okay. Yes, you're right.
Because there's so many things I don't understand here.
Okay. So it's not simple statement, but I would like to tell about some generalization of this statement and some arguments for this statement. Also, I would like to add the following description. 6 points on the conic is parameterized by Fano variety Igusa quartic. It's famous quartic. Fano three-dimensional.
Do you know the name of this Igusa?
Igusa, yes.
I mean, there are 2 Igusas at least, the father and the son.
Maybe father, I think. So I don't know that there are 2 Igusas. So.
Yeah, the son is pretty famous as the father.
So okay, this variety is classical. Maybe it's singular, it's rational, it's There are many works about the geometry of this variety. So I would like to tell about configuration point in a projective space and its moduli. So we would like to consider the following Git quotient. As we know, two sets of orthogonal projectors are parameterized by the set of 2r+2 points. And the action of GL, general linear group in this case, correspond to action of projective general linear group in this case. So we can consider quotient of this data by general linear group, and we can consider this data by action of projective general linear group. It's the same. So moduli this Git quotient is quotient was studied by Dolgachev and Ortland, and they find some description of this modular space. So I would like to recall the construction. It's a famous work of Dolgachev and Ortland. Assume that we have 2r+2 points and consider their matrices, coordinate matrices M. It means the following. I write in columns coordinates of these points. It's matrices 2r+2 by r+1. There are 2r+2 columns and r+1 rows. Columns correspond to points and rows correspond to their coordinates. So we consider this object, and Dolgachev and Ortland proves that coordinate ring of this variety is generated by so-called tableau functions. So I would like to tell about this object, about tableau functions. So I would like to recall the following semi-stability condition. So if you know something about invariant theory, we cannot.
What does this have to do with tableau function?
I will tell about later about tableau functions. I would like to speak about some condition of semi-stability. So we can't take all this projective space. We have to to take some open subset. So its open subset denoted by P2R plus 2R SS, semi-stability, and the condition of semi-stability is the following. Condition of semi-stability of this set of points is semi-stable. Maybe so. I would like to write so x r2 r plus 2 is semi-stable if there are two subsets xy1 xy r plus 1 to non-intersect subsets xj1 xj r plus 1 such that these subsets, these points correspond to basis of vector space basis of V. V is so PR is projectivization of V. We have R plus 1 one-dimensional subspaces in V which are linear independent.
So you do assume that these two R plus 1 tuples of points are disjoint?
Sorry, disjoint. Okay, that is of course it's x1 x2 r plus 2. Yes, yes, yes. It's true. What is a tableau function? Tableau function a function of the following type. Tableau function is a product of minors of r plus 1 of M, of matrices M, minors of M. R plus 1 minors of M. And they satisfy the following condition. Each column each column occurs in tableau in this product if each column occurs in this product d times, then tableau function has is homogeneous of degree d. And this tableau function, each column occurs the same times, and these tableau functions define the embedding of this quotient in some projective space, maybe weighted projected space. This embedding defined by a tableau function.
What is tableau function?
It's a product of minors such that each column occurs the same times. So I will consider some examples. Examples. First example. Consider the case when R is 1. In this case, we have 4 points in P1. 4 points in P1. It's it's well-known object. This object is called J invariant. So as we know, 4 points are branch divisor of elliptic curve, and so this variety parameterizes elliptic curve. But we can. I would like to write tableau functions. There are 3 tableau functions. 1, 2, 3, 4. 1, 3, 2, 4. I will explain what does it mean. Consider 4 points. For example, x0, x1, y0, y1, z0, z1, w0, w1. It's 4 points in P1. So consider coordinate matrices x0, x1, y0, y1, z0, z1, w0, w1. 1, 2, 3, 4 tableau function of this type is equal. I have to take this minor and this minor. It's a product of these 2 minors. 1, 2. I have to take first 2 columns. 3, 4. Yes.
Does order make difference?
Yes. Yes. Of course. Order is important. Okay. I fix the order. Okay. Order is important in this case. So we have
3, 4, and 1, and 3, 4, 1, 2. Isn't it the same?
this. Sorry.
I mean, 1, 2, 3, 4, and 3, 4, 1,
Okay.
2.
Okay. It's the same. Okay. Okay.
In this sense, the order is not important.
Yes. In this case, yes. But I think that in this case, it's important. Okay. So we have
And take a third product, a third element, right?
we have 3 elements.
And
Yes.
I mean, you can actually define a product of 2 functions. Of 2 tableau functions will again be a tableau function, right?
So we have the following Plucker relation in this on this tableau function. So maybe I continue here.
Sorry, just one question. It seems that tableau functions give you some subset of Plucker coordinates.
Yes. Okay. In this case, yes.
And, does it give enough?
Sorry, but these elements are not numbers. This is coordinate in P1.
Yeah.
X0, x1 is homogeneous coordinates.
Sure, and that's why you get made it not into CM, but into projective space, right?
Yeah.
What does W mean?
Yeah.
W, this?
Yeah.
I will consider the following example, and you can. It means weighted projective spaces. Wait.
So the theorem is that.
Sorry, I would like to finish this example. We have P14. This git quotient is isomorphic by 2Q1, and we have the following condition on this tableau function. It's a Plücker condition. Plücker relation. The condition relation. So let us consider the following example. It's a 4-point in P2. P1 is lower index. Example 2. Example 2, R is 2, and we have to consider the following quotient. It's a 4-dimensional variety. So we have the following tableau function. Z0, oh, okay. 1, 2, 3. First.
Actually, it corresponds to all possible decompositions of 6 tuple of points into two 3 tuples, and so maybe there exists another tableau function. In this case, I will write another tableau function. So as you say, there are tableau function of simple type.
But you consider only the tableau functions of degree 1, right?
Sorry?
You consider only functions of degree 1 in the definition.
Yes.
Right?
Yes, it's of degree 1. Okay.
Yeah, but not, why not of
In this case, there will be of high degree. Sorry. I will denote it by Z0, Z1, Z2, Z3, Z4, and we have the following of degree 2, the following tableau function of degree 2. So we have. Sorry?
There should be 6.
1, 2, 3, 4, 5. Yes. There is some relation between this.
I mean, the number of simple tableau functions. They should be equal to the number of ways you choose 3 elements out of 6. Right?
Yes.
So that's how what is this minimum coefficient? 20.
But there are some linear relation between these tableau functions. So I write only linear independent. Okay. So this relation like this, something like this.
So you gave us linear independent.
So what's the relation between?
That's why this function y is independent of all previous ones. Otherwise, it would
It's linear independent, but not independent. I would like to write the relation between y and zy. So there is the following relation. So y is degree 2, zy is of degree 1. So we have the following embedding in P in the following weighted projective space. We have one variable is of degree 2 and 5 and 5 variables of degree 1, and this variety is given by this relation. So this variety is famous and it's called Koebel variety. Koebel variety. Its variety is parameterized, parameterizes 6 point in projective plane, and so this Koebel variety I denoted by C. We have the following map, surjective map on projective space P4, generate these coordinates Z1, Z2, Z3, Z4. It's this map has degree 2, so and ramification divisor is a Gusse quartic. Ramification divisor of this map is a Gusse quartic. Ramification divisor. We have involution acting on Koebel variety, and this involution is called Gale involution. Gale involution, maybe Koebel involution. There are maybe so let us back to projectors. What does it mean tableau function in terms of projectors? So I would like to explain it. It is well-known result that so I would like to erase the board. Okay. If we have this data, one-dimensional projectors, orthogonal one-dimensional projectors, then and we will consider, we would like to consider the ring of invariance of this variety by GL R+1. It is well known that the ring of invariance is generated by traces of the following type. And so on. What? Yes.
You get all this even number of factors in the choice, right?
Why even?
Yeah,
Why?
I
Why?
mean, is it true that you only consider these traces, these kind of traces? Is it possible to consider something like Pi, Qj, P, K?
So we can remember the property of traces. So using orthogonality, we get that this is 0. So also these projectors are of rank 1, and we have the following condition. This is because Py and Qj are of rank 1. So it's so we can get some less number of these traces. So what does it mean, these traces, in terms of this tableau function? So I would like to tell about only the case of RS when R is 2. So E and in this case, trace of P1 Q1 is the following ratio. And so on. Yes. And also, I would like maybe I would like to write the following trace. It is y divided by z0 square, and this is z1 by z0. So any other traces has the following form, and so this trace has the following form. So there is some relation on traces like this, but I didn't. I wouldn't write it because it is not important. So now I would like to tell about self-associated configurations and commutators. So how many times?
We're supposed to stop at 8 at the latest. So it has about 1 hour.
So maybe it will better to tell about some symplectic variants of this problem. Let us symplectic story.
So trying to classify NBB.
So
You can try to classify NBB using Algebraic geometric approach. We just classified intervals of points in projective spaces.
yes.
And of course there should be some special properties of these intervals when we pass from generic basis to these MUBs, right?
No, MUBs. I will tell it later on some application to MUB. Maybe we can think about it. That it's some more general problem which from MUB or from classification MUB. Maybe some generalization of this problem. Symplectic story. Maybe I tell about it. Consider as early consider two systems of projectors, and assume that this orthogonal, but this we not assume that this orthogonal, not orthogonal. Assume that this projectors we fixed Py. In this case, we fix algebraic torus generated by this Pi. Let T be algebraic torus. And consider all these projectors. Consider the variety Y, which is a product of coadjoint orbits. Or Q1 is a coadjoint orbits of projector of rank 1. Of projectors. we have the following Hamiltonian actions on this.
So this torus is just a subgroup in GLM.
Yes.
Okay, because
We have, yes, this torus. You mean this? Consider action of TR plus 1 on Y. We have standard symplectic form on this variety, constant Kirillov form. This variety is symplectic, and in this case, this function define integrable system on Y. It means that Poisson bracket of this two function is 0. This function are in involution with respect to standard Poisson structure on this symplectic variety. So we have a momentum map. I will denote it by mu1 to here. So we have it's some it's some calculation, yes. We can consider some we can consider this form and deduce from this that they are in involution. We have some relation on this function. Since these projectors are orthogonal, then we get that trace pi qj for I1 is 1. Sorry?
What particular sort of Poisson structure you use here?
I use standard Kirillov form, constant Kirillov form on this. Okay.
Maybe you need to embed everything into co-adjoint representation. I don't see how you do this.
You would like to get exact formula?
No, I just need to.
So,
Q used to be just.
So,
a
yes,
it
I
is
can see
not
the coadjoint.
It is not in the algebra. It is not in dual space of the algebra.
Okay, using trace form on
Correct.
G, using trace form on GL, on algebra, only algebra. There is a non-generate trace form, so I can get the following identification. And so, using this identification, we get that. Maybe I finished. Using this identification, I can identify coadjoint orbit and adjoint orbit. So, product of symplectic varieties is symplectic varieties. So it's well known. So
I'm sorry, but again, coadjoint orbit is the orbit with respect to the action of the whole group.
okay,
Not of the torus.
using this identification, we get.
But it is the coadjoint orbit is the orbit of a point with respect to the action of the group, not with respect to the action of the torus.
TR plus 1 is an algebraic group.
Yeah, but it's not the group which is used to define the coadjoint orbits.
We can consider the action of this group on this, and we can check that this action is Hamiltonian. So we can find the following set of function, and we can consider the following The following map. This map is a moment map under the action of this group. So we have another action. We have another moment map. Maybe you mean this to Lie algebra GL R+1 defined by the following correspondence. Q1 QR+1 maps to sum of QY. We have two maps. Now we can consider the following subvarieties. Consider subvariety Z, which is we fix this in this identity element and consider its preimage in Y.
What is F?
R+1. These functions are linear dependent because we have the following condition. So we have R+1 condition. This function R+1 square, R+1 square minus R+1. We get this. Consider this. This variety, it's parameterizes orthogonal projectors. So it is a well-known fact that if we have the following identity, then QI are orthogonal. It's some fact from linear algebra. So if and only if. So in this case, we get then Z is a moduli of orthogonal projectors. So we would like to consider the following subspace. Let us restrict mu1 on Z. Sorry?
I'm sorry, before we proceed, in order to get this second map.
Second map is
mu2.
yes. It's defined.
GL R+1 on Y.
Okay. GL R+1. Yes. I take it.
GL R+1 doesn't act on Y.
Doesn't. Sorry. This is a map. Moment map under action of GL R+1 simultaneously conjugation by simultaneous conjugation on Y.
It actually takes us away from the orbits of the torus.
We have two action. This group and group on Y. So maybe I didn't understand what do you ask?
So O is not the orbit with respect to the torus action.
Yes, mu2 is standard moment map for products of. Okay. I would like to consider this map, the restriction of this map on Z. And I would like to consider differential of this map. And we have the following identification. Значит, sorry, maybe I denoted mu1 prime, differential mu1 prime. And I fixed the point Q from Z. and consider a differential of mu1 prime in the point Q. In this case, we have the following identification. Where TQ is Cartan subalgebra of GL R plus 1 corresponding to Q. It means that it's Cartan subalgebra generated by projectors corresponding to Q. T is Cartan subalgebra of torus T. This subspace is orthogonal complement with respect to standard trace form. Also, I would like to tell about. I would like to formulate the following proposition.
Yeah, you mean TQ is generated by these QIs?
TQ generated by these QIs, T generated by PIs. So we have the action of torus on Z, and when we consider the quotient of Z by torus T, denoted by X, and in this case we have two sets of orthogonal projectors, and fix some point U. In this, X parameterizes two pairs of orthogonal projectors up to action of GL. And we have the following identification. The mu1. Consider we have we have the following decomposition of morphism from Z to F R plus 1. Z parameterize orthogonal projectors, and in this case we have additional condition on traces of the following type. Zero, and so image of Z is in the FR square. So we have addition R linear equations, and thus R plus 1 minus R, we get R square. So we have the following decomposition of this map, mu1 prime, and consider the following map. This map may be denoted by mu1 2 prime. This map has the following identification with TP is Cartan subalgebra generated by PI. TQ as usually by QI, and so this means that we get that we get that we take orthogonal complement up with respect to trace form.
Just summing up, I actually lost the thread just a couple, 10 minutes ago at least. But
Okay,
just
maybe I
what
can.
I can understand. You explained the way one can encode two pairs of orthogonal bases in terms of the symplectic geometry. Is this
Okay.
true or not?
Okay. So
So,
I would like.
Yes or no?
Yes.
Okay, thank you.
Symplectic geometry helps to get this identification. I would like to tell about okay. Let us back to orthogonal projectors. What does it? Okay. Consider Z2. It's moduli of two sets of orthogonal projectors. How is defined this map mu1 to prime? As we know, the ring of regular function on this is generated by traces. And this map is defined by only by the following rule. Trace pi qj. So we have the following map, which is defined by these traces. If we consider the following point as 0, 1 r plus 1, 1 r plus 1, we get that mu1 to prime minus 1 as 0 is parameterized MOOPs. Recall that condition trace py qj is 1 divided by r plus 1 define algebraic version of MOOPs. Another question is what's the property of this map mu1 to prime? So it is well known that mu1 to prime is dominant.
What?
Dominant. It means that it's something like surjective. I think that this map is surjective, but I can't prove this. So, but dominant, it means that image of this map is dense in this subspace. It's some definition from algebraic geometry. mu1 to prime is dominant. Probably surjective. It's a question. It's open question. In the case of R1, it's isomorphism. Case R is 2, it's 2. It's degree of mu1 prime is 2. It's in R is 3. Degree of mu1 to prime is 12. It's number of point in the preimage of generic point. Generic point. In this case, if we consider point corresponding to MOOPs, as I said earlier, there is a one-dimensional family. It's a curve blow down in the point.
What is the structure of that model at C, and what is the geometry?
This? Yeah. What is geometry? In the case RS2, it is an open subset of Cobol variety. In general case, it's open. It's Z is it's open subvariety of this quotient, G quotient. No, there are many singularities. No, I can say about something else, but I think I haven't time. So
You have how
30 minutes.
It's about
40 minutes,
30.
30 minutes.
how much time do you
Okay, I would like to speak about some algebra in this context.
how much time do you need?
No, I would like maybe 15 minutes. Okay. So I have many. Okay. I would like to speak about some algebra. Consider the following algebra. Fix point x in P3. Consider algebra generated by the following elements. Identity and P1, P2, P1, Q2. P1, P2 are orthogonal and are projectors. Analogously, Q1 and they are projectors too. Its algebra is a free product of these two algebras, F plus 3. And, sorry?
It's non-commutative.
It's not commutative, it's free product.
I mean, the algebra of what?
F plus 3 is commutative,
No,
of
I
course.
understand, but he said its algebra. What does it mean, its algebra?
This algebra, I would like to consider this algebra and this.
Created by this.
I denoted by B. I would like to consider algebra X, which is quotient of this B by ideal generated by element S. Element S is is a sum of commutators. I fix point, and for this point I consider element S and consider the quotient of this free product by ideal generated by these elements. So what can we say about this algebra for generic X? We have the following answer on this question. Theorem for generic X from P3, algebra AX has dimension 18. AX is semi-simple, and AX isomorphic to C. C plus 9 plus algebra of matrices 3 by 3 over C. What does it mean in terms of varieties? It means the following. I would like, it means that for generic X, this algebra has one three-dimensional irreducible representation, only one. Reducible three-dimensional representation. And it means that we have the following map. Recall that I denote Igusa variety. Igusa variety in this context Igusa variety. This variety parameterized all projectors of corresponding to some this relation. As I say early in the start of my talk, parameterizes all projectors P1, P2, Q1, P2 with this relation. How we can to see this Igusa quartic in terms of this algebra, or maybe in terms of this element. Consider the following quadric in P2, which is given by the following equation. Why this equation? In this case, this element can be written in the following form. S is S.
Yeah, we parameterize all projectors with this relation, this fixed X.
No. Parameterizes all projectors for which there is some relation of this for some x, y, j. If we consider in P3, if we have the following condition on the point x, S can be written in this way. Oh, one can check that it is on by P1, Q2, and please add to B2, P2, Q2. So we can see that product of this is equal product of this. So what does it mean in this case? It means that if for generic point of this quadric, all Pi and Qi commute for generic point x from Q, Py and Qj are commutes. Because if this element commutes, then the squared is commutes, and so on. We get that all Pi and Qj are commutes.
Sorry.
No,
The point for generic point in this quadratic form.
in quadric, yes, means that Py and Qj are commutes. Are commute. So we okay. Let us check this.
For generic point,
I mean that from this,
if you take an element in S,
if we have the following correlation,
generic point.
x,
I see.
okay, it means that if we have the following condition, it means that Pi Qj commute.
What is Q then? I just don't see the definition.
Q, sorry,
What is Q? Capital Q.
capital Q.
It's a quadratic.
It's quadric defined by this equation.
But
Quadric
P1, how do Pi and Qj?
Pi Qj
How are they referred?
for all I j.
I mean,
Pi Qj it's projectors of rank 1. We have the
if you take a generic point in the quadratic,
in quadric,
if you take the points,
then that point x, which is this point can help us to define element S, the relation on
in this algebra.
yes. If we consider the quotient by this relation,
Oh,
we get that Pi and Qj are
commute in this quotient.
commute in this quotient.
Oh,
Yeah, okay.
okay.
Yes. I'm sorry. But not for all points in quadric. There are the following curve on quadric. Its curve is given by the following equations. Maybe I omit these equations, but we have this reducible curve, which is the union of 6 lines, for which there is something like the following condition. Maybe P1 commutes with all Pj, but all Qj, but P2 is not commute. This configuration is famous, and Corrado-Segre proved the following fact. If we blow up this curve and blow down Q, quadric Q, we get Segre cubic, which is projective dual to Igusa quartic. So this map from P3 to I is the following. We have to blow up this curve, blow down this quadric, and after this we have to take projective duality. Oh, maybe it's technical result, but in this context, one can see some geometry, some algebraic geometry in classical sense. So Corrado-Segre, it's Italian algebraic geometrist. So it's all. I can't to talk about something else, but I think that it's sufficient. Thank you for invitation.
What are your plans to explain more? You can just explain to us. I remember your paper was really big.
My paper is not is unpublished yet because there are some technical details. So I write and rewrite it more and more. So
Yeah.
it will be a joint work with Anna Kocherova. So these results are from this our joint work with her. So
And what was the results of the first paper you mentioned at the beginning?
first, symplectic geometry, maybe it's from our work with Bondel. Degree of mu prime from joint work with Guminov. So it's some. There are many works with my friends. My talk is based on 3 or maybe 5 articles.
Are there some relations with Algebraic model spaces?
I think I can find it, but yet I don't find it. So I didn't find it. I think it must be. It must be true, of course.
A very stupid question. When you have symplectic structure, you can always speak about some quantization. You actually begin with some quantum.
Okay.
So I
Yes.
just wonder whether there is anything you can tell us in this direction. For instance, you have symplectic manifold, symplectic space, and you know that the algebra, say, differential operators on this symplectic manifold, that is just the same thing as the quantization.
I understand. Yes.
Coincides with some important quantum system. I don't know, just something.
I don't know. I don't know about it. So maybe it's a good question, but I haven't answered on this question. So of course, maybe this quantization, maybe of course, if you have symplectic variety, and so it's very
Well, for instance,
right question about this.
non-cumulative algebra. This non-cumulative algebra.
Okay. Yes.
Anything to do with it?
Okay, but I don't think about it. So I think it's a right question, but I haven't time for this.
But actually, it seems that you just, well, if you forget about the first condition that P1 times P2 is equal to 0,
Mm-hmm.
and if you just forget about this, and then
These two?
Yeah, this. I mean,
Okay.
You're just two commutative algebras, not necessarily even the
Oh,
projections,
so
right?
you would like to?
Yeah,
Okay.
then it looks
Okay,
like
okay.
the Abad algebra. If you just, well, but when you add this relation,
You would like to consider this? Okay. Then
Yeah.
this.
and also you can also even forget about the
Projectors.
the-
Okay. Okay.
Yeah, but then the condition downstairs is something like the commutativity condition. You impose some commutativity, for instance. in just-
Okay. Yeah. It's something like, yes, of course. But yes. It's.
But can you explain why there is C3 and on the left? On the right, C3 follows from Q1, Q2, and Q1, Q2. There are 3 elements in the algebra created by Q1 and Q2, right?
No. C plus 3 is a subalgebra generated by Py and 1, and
so
this
one.
is
But
Qy
somehow
and 1.
seems
Yes.
to be common for both algebras.
Yes.
But I understand there should be C2.
C3 1.
So 1 is not supposed to commute with Q1 and Q2.
Okay, it's free product over subalgebra generated by
Oh,
1. Okay.
okay. And
I omit it because I think it's standard notation.
Could you recall what was the main aim of your paper with Bondel?
It's about our paper is named Symplectic Geometry of Unbiasedness, and so we we take in these articles all symplectic geometry which we find in the unbiasedness. There are many other concepts in our article. So this article was the aim of this article was formulation of some conjectures, maybe like this, and
about
mutual.
classification.
Oh yeah, about mutual unbiased basis, and maybe find some connection between symplectic and algebraic geometry, and so on. It hasn't a revolutionary results. So,
Revolutionary results are very rare.
okay.
Yes, we all want to
Sorry. Thank you very much for your attention.
Можешь тогда снять. Он был тут, да?
Нет, он не пришел тоже.
Я звал на свою конференцию в 50-летие как раз, но я там жутко заболел.
Да,
Очень обидно было.
ты то же самое хотел.
Да, конечно, да. Там причем. Вот уже даже написал все, как бы вот тут как раз эти коники были так.
Ты
Ну, заболел прям, и я писал
злым ковидом заболел?
Да уж нет, это только сходила в школу, притащила,